Hello, it's Dr. Daystorms, and in this section of Chapter 10, we're going to start to discuss the kinetic molecular theory and use it to start to describe what can happen as the conditions for a gas change, and ultimately see how a gas will deviate from the ideal gas law and utilize this in what's called van der Waals equation. So first off, we have kinetic molecular theory, and what you can do with kinetic molecular theory. Let's imagine that we have a container. It contains some gas. Those gas particles are just moving around. They're bouncing around all over. They're bouncing off of each other. They're bouncing around the sides of the box or the container that it is. And then if you increase the temperature, they're going to bounce around faster. If you decrease the temperature, they're going to bounce around slower. Okay, so this allows us to start to understand or to estimate what's going to happen to these gas particles as the environmental conditions change. Okay, so the main tenets, the main ideas behind the kinetic molecular theory is that you have this gas that consists of a very large number of molecules, and they're just in a constant random motion. It's not static. It's a very dynamic process. And so you can make a couple of assumptions here. One is, let's say that we have this container and it's full of these gas particles, but the gas particles themselves are so tiny compared to the volume of the space in which they are in, or they reside. Okay? And another assumption we're going to make is this idea that the particles themselves are neither attracted nor repelled by each other. Okay, so that way they're just bouncing around randomly. And if you do that, you can think of it ideally, and we would get the ideal gas equation, P inert. Okay, so to reiterate, we have this idea that the combined volume, so the molecules of gas, is very small relative to the container, the volume that's contained in, and that the attractive or impulsive forces between these molecules are negligible. Okay? So what happens then when a molecule hits another molecule and they're traveling really fast? So what's going to happen is that one molecule will absorb, or will take the energy from the other molecule whenever it hits. However, if you add up all of the molecules in the container, we add up all of the energy, even though it's being transferred from molecule to molecule at any time, the average energy of those molecules as a whole does not change with time as long as temperature doesn't change. So that's the one caveat here, is if the temperature remains constant, then the total average kinetic energy of this collection of gas, it does not change. Okay, the individual molecules themselves may have different changing, fluctuating energy levels, but at a macro scale, it doesn't change. So what happens if you change the temperature? Well, just think about what happens if you start to add heat to a gas. It's going to increase. And so what this graph here is showing is it's looking at the fraction of the molecules that have a specific speed of 10 meters per second. Okay, and so they've marked out on this graph that if you're at 0 degrees, and that's what the curve looks like, and you're looking at a specific fraction of like how many of the gas molecules are traveling at a very specific velocity, have that much energy, that much kinetic energy. Well, then what happens is if you if we heat up those gases to 100 degrees, then what's going to happen is that there's a higher percentage of them traveling at that faster velocity. Which that just makes sense. What it's saying is if you add temperature, if you heat something up, it's going to go faster. Okay? So then we start talking about the real gases in the real world, and many times, under most conditions, they are not ideal. In fact, they are only ideal at either really low pressures or in really high temperatures. So the idea is if we had 1 mole of gas, and you take PV, you divide it by RT, it should equal to 1. Well, what we can see here is that these gases only behave ideally at really, really low pressures. And then they can change. They don't even have the same characteristics. So for example, if we look at hydrogen, you keep adding, the pressure increases, it increases relatively linearly, whereas if you look at the way that carbon dioxide is, as you add pressure, it actually deviates and decreases the ratio. Then it starts to increase to about 500 atm, where it reaches 1 again, and then it goes beyond, it goes in higher. And so it's due to this idea that the volume itself really is not completely negligible, and there really are attractions or repulsions between gas molecules. Okay? So anytime you go to either higher pressures or lower temperatures or the both, you're going to deviate from the assumptions that we have been making, and you are no longer going to abide by P-inert, the ideal gas law. And so instead, we have to make certain corrections. One correction that we're going to make is that you have to take into account that there is an intrinsic volume. Those gas molecules really do have a volume. It's just really tiny, but it does have a volume. And secondly, gas molecules themselves are going to have an attractive and repulsive forces. Okay, that's quite possible. When you put this together, you get what's called van der Waals equation. This is a van der Waals equation. I will give you this on the exam. And you can see it does look a lot like P-inert. We have a P times a V, entity, and it equals nRT. So it's a modified gas law. I would also give you this table, but this just shows you, like, for certain gases, they have figured out the A constant. This is the constant that helps account for the changes in volume in attraction, and then we also have the B constant, which alters the volume entity in P-inert. Okay, and so literally, once you have this table, it's just a case of plug and chug. And so, for example, if you're talking about H2, N is just the moles squared, and V is, of course, volume. So as long as you know P, N, V, R, and T, you just have to look up the values for A and the values for B, and then plug it into the equation. Okay, so let's just look at this example. We have 1 mole of an ideal gas. And if 1 mole of an ideal gas was confined to 22.41 liters at 0 degrees Celsius, it would exert a pressure of 1 atm. Use the van der Waals equation and the constants in table 1013 to estimate the pressure exerted by 1 mole of chlorine gas at 22.41 liters at 0 degrees Celsius. Okay, so you have to be able to look back at chlorine gas. So if we look at chlorine gas, there's chlorine, 6.49 is the value for A. The value for B is 0.0562. Okay. So now we're going to utilize the van der Waals equation, and we need to manipulate it in order to solve for pressure. So let's go back and I want to actually explain how they got this equation, how they got to this point, okay? So let's just go back to look at that. So the equation was this: P plus n squared A divided by V squared times V minus NB is equal to nRT. The question was asking for us to solve for P. Okay, so you're first going to need to divide by this entity. Alright, so we're going to divide both sides by the V minus NB. And when we do that, we get P plus n squared A divided by V squared is equal to nRT divided by V minus NB. Now all we have to do is subtract this from both sides. So when we subtract that from both sides, we get P is equal to nRT, and R is just the gas constant that we've been using, divided by the entity V minus NB. That's an N. It doesn't come across very well. Minus n squared A divided by V squared. So then you literally just plug and chug everything in. A and B are just constants that you look up and get from a table. Alright? So A and B are just constants that you get from a table. R is just the gas constant that we've been using. T and the V's, V and the V, those were given to you in the equation. So let's go ahead and look at this up. Okay. So, as I mentioned before, we're just going to be plugging and chugging. So we have 1. Oh, that didn't come out right. 1 times 0.0826 times the temperature, 273, divided by 22.41 minus 1 times 0.0562, minus this entire entity, which was n squared, which is 1 squared, times 6.49, that was given to you in the table, divided by 22.41 squared. When you do this, you're going to get an answer at 0.99 ATM. Okay, so an ideal gas is 1 ATM, whereas the chlorine gas under these conditions is really 0.99. This makes sense because we are under conditions at a low. We are under these conditions where it wouldn't deviate too greatly from the ideal gas law. Okay? So it seems very reasonable. Any time that you're going to use the van der Waals equation, once again, you just need to look the values up on the table for any of the gases. I would never ask you to try to derive your own constants, because that just really would be beyond the scope of this class, and also it would just take too much time to do for a quiz or for an exam. So hopefully this has helped explain how to figure up or use a gas law whenever the gas is not under ideal conditions. I'll see you in class.